Yes, thank you, Marcelo. I want to thank the organizer for inviting me to give this talk at this night conference. This is one of my favorite conferences where we can meet with friends and discuss in a pleasant atmosphere. I would also like to thank the organization of this edition of the event in this context of pandemic, and I hope that we can meet in a face-to-face meeting next time. I'm going to talk on an entropic characterization of quantum state with maximal evolution. This work was done in collaboration with Andrea Valdez Hernandez, Cesar Maglione, and Angel Plastino. And to begin with, I will try to motivate the introduction of a measure of the amount of evolution, which is the measure that we maximize in order to obtain these optimal states. There are several questions one can ask when analyzing the limitation associated with quantum evolution. An important question is, for how long does one have to wait in order to see something happening? And another question, which is related to this question, is how fast can a quantum system evolve to an orthogonal state? And this is the basic question addressed by studies on the quantum speed limit. Our alternative and complementary question is how much happened during a certain period of time. This second question is the question I will address in this talk, but let me first comment briefly some ideas behind the quantum speed limit. The problem of optimal evolution has attracted a lot of interest. That is because besides intrinsic interest as a fundamental question, the time limitation associated with quantum evolution also have practical implications. Several work focus on the limits imposed by the basic laws of quantum mechanics in the speed of information processing and information transmission. This is the basic scheme. We have here the initial state, psi 0, which evolves unitarily to an orthogonal state in a time tau. This is the orthogonality time, and this time can be regarded in the context of quantum computation in the computational state needed to perform some quantum process. This orthogonality time is connected with several fundamental aspects of quantum physics with important quantum implications in the field of quantum information. And the concept of distinguishability, because it's the time to evolve from between two distinguishable states, the concept of distinguishability appears here, and this concept will have a central role in the talk. So the first answer to this first question, came with this work in 1945. The work was by Leonid Mandelstam, who died before the article was published, and his student Igor Time. They derive a kind of uncertainty relation between energy and time, and that bound the time of the speed of evolution in terms of the spread of energy. Several years later, indeed 53 years later, a second answer came with this work by Norman Margolis and Lev Levitin. They derive another bound which is independent from the Mandelstam bound, in the sense that the Mandelstam bound cannot be reobtained in terms of this other bound, and they bound the speed of evolution in terms of the mean energy of the system relative to the ground state. So the Mandelstam time limit was introduced as I said before, as an uncertainty relation between energy and time. And even it is not crucial for this talk, I prefer to distinguish here between bounds and uncertainty relations. Also for completeness, I want to mention this work, also in the 90s by Anandan and Aharonov. They rederive the Mandelstam time limits on geometric foundations. And according to this work by Anandan and Aharonov, the Mandelstam time limit can be interpreted as a comparison between the path followed in the state space with the geodesic endpoint of that evolution. Here are the two bounds, and more recently, in 2009, Levitin and Toffoli introduced a unified version of the bound that take this form, and this bound is tight, and this expression is one usually used in problems in this field. So to address the second question, I will try to explain why we think this is an interesting question and even more a necessary question to be answered. So when studying problems related to the speed of quantum evolution as measured by the orthogonality time in systems evolving continuously in time, there are at least two points or two observations that we need to bear in mind. One is that most of the initial state never evolve into an orthogonal state. In fact, the subset of the initial state that do evolve into an orthogonal state is a subset of measure 0 in the state of all space. And even for those states that do evolve to an orthogonal state, the number of times that the system reaches a state orthogonal to the initial one in an interval of finite duration is itself finite. So from these two observations, we can conclude that tau, the Biot's grid conceptual value, is not directly applicable in many relevant physical situations. So an alternative procedure, because this tau cannot be used to characterize the speed of evolution of many states, because, for example, this time is infinite for many states and then cannot be used to characterize the speed of evolution. As an alternative procedure, one can study the time needed to reach a state having a different value of the overlap, that is not the time to reach an orthogonal state, but the time to reach a state with a given different from 0 value of the overlap. But in contrast with the case of 0 overlap, there are not mathematical or physical reasons to choose one value of the overlap as a more fundamental than another. So it's very difficult here to put some conditions, and maybe it makes sense to explore different possible values, an approach that takes into account different possible values of the overlap. And that is what I'm going to tell you in this talk. So this is the outline of the talk. I first will introduce the amount of quantum of evolution. I will discuss some properties of this measure, and I will show the behavior of the measure for some typical simple quantum systems. Then I will show you a relation of this measure with the timeless approach to quantum dynamics. And through an entropic approach, we will see the quantum system that optimizes the quantum evolution under constraint given by a fixed mean energy. And to finish, I will present some discussion and final remarks. So the notion of distinguishability between quantum states is of particular importance in quantum information and in quantum computation. In this is this concept of distinguishability, which leads to the idea of a kind of orthogonality. And this distinguishability can be quantified between two pure states with the square overlap of the state. If the square overlap, the square modulus of the overlap of the state is equal to 0, then the two states are perfectly distinguishable. This corresponds to two orthogonal states. And on the other extreme situation, if the square modulus of the overlap is equal to 1, the two states are totally indistinguishable from each other. That is, indeed, that these states represent the same physical state of the system. So our approach is based in the idea that a pure state takes different degrees of distinguishability. And in short, we propose a measure which is a complement to the time to orthogonality and to the time associated to the number of computational steps, to use a measure of the amount of the evolution of a system given by the average distinguishability of the system as the system states, as the system evolves. So we define a measure in terms of the average of the time average distinguishability of the system. So this is the quantity that we propose to quantify the amount of quantum evolution. This quantity is defined in an interval T1, T2 of length capital T. And here, phi t and phi t prime represent two states of the system at different instants of time, t and t prime respectively. And this average distinguishability provides a quantitative assessment of how diverse are the states that the system visits during this time interval. So high values of t, that is values close to 1, means that these two states are highly distinguishable or can be perfectly distinguishable. And on the other hand, low values of d close to 0 means that means a low variation between the state of the system at time t and at time t prime. That is, this overlap is close to 1, and then this measure is close to 0. So if we now consider this measure and move the interval of time, that is, we consider the measure d in the interval t1 plus delta and t2 plus delta, we reobtain with some algebra that I don't show you here, we reobtain the same measure. So this measure d depends on the interval only through the length of the interval. So we can write the measure in this more simple way. This capital T is the length of the interval, and without loss of generality, we can write this integral between 0 and t. So this measure d does not depend on which time window we are looking at, but only the size of the window. So this has a time translational symmetry. And this is a nice property of the measure. So now to go deeper in the form of the measure, which we do is to write this state phi t in an appropriate configuration space basis x. We can represent this state in this way, where here x represents some spatial coordinate or any other degree of freedom of the state. And this is the wave function which satisfies, as usual, the Schrödinger equation. And it can be expanded in terms of the orthonormal eigenfunction and the eigenvalues of this Hamiltonian H here. And this coefficient satisfies a normalization condition as usual. If you put all together, this expression here and this expression here, we can compute this amount of evolution with this form. And we can integrate, and we obtain this final expression from the amount of evolution that experiences a system in a time interval of length capital T. Where here we define this omega nm as the difference between two different energies, En and Em. So this expression has two contributions. One here, this first term, which only depends on the coefficient of the expansion, that is only depend on the initial state. And this other contribution, which is an oscillatory term, which depend on the length of the interval. So we can define an asymptotic limit for this measure, which is the limit of this measure when this capital T goes to infinity. We call this asymptotic value DL, and we can prove that this measure is always less than or equal to its asymptotic value. And I will show you now with some examples, because it's more, I don't know, easy, some illustrative examples, the behavior of the measure in terms of this time, t, and how the measure quickly reaches its asymptotic value. So we compare the time scale associated with the measure d with other relevant time scale of the system. For instance, the dynamical of the system characterized by the behavior of the autocorrelation function. So this is the autocorrelation function. It is defined as this overlap. And we compute here both functions, the autocorrelation function and the amount of evolution for a qubit system. So here we have this two-level system, right in terms of the this orthogonal eigenfunction phi1 and phi0, with two eigenvalues, E0 and E1, and with this coefficient A0 and E1, which satisfies the normalization condition. So we can compute the autocorrelation function and the amount of evolution, and we see here that the amount of evolution quickly reaches. These figures are in terms as a function of the capital T over TC, where TC is the natural period of the system. And we see that the amount of evolution quickly reaches in all cases. These different cases correspond to different values of this coefficient A0 here. And in all cases, the asymptotic value is represented by this dashed line here. So in a time which is close to the characteristic time of the system, we can see that the measure reaches the asymptotic value for all cases. So we also consider an harmonic oscillator, showing that in a period of the autocorrelation function, the amount of evolution again reaches its asymptotic value. Here we have a T-level system. We consider different values of T equal 4, 8, and 50. And we see that this measure D, we can show that this measure D is maximal in the equally weight case, that is when all the coefficients of the expansion are equal to 1 over square D, where D is the number of levels of the system, and that the measure increases with the number of turns with the number of the turn in the expansion, or which is the same as the information regarding the particular energy eigenstate decreases. This curve corresponds to 4, 8, and 50 levels in the expansion. We also consider here a 2-qubit system, which is a 4-level system. Here we consider a degenerate spectrum of energy, and we obtain a similar result. The measure D reaches or almost reaches its asymptotic value in a time related to the characteristic time of the system. So to finish this part of the talk, we consider a wave packet in an infinite one-dimensional potential of length with width L. If the initial state has this form, is a Gaussian packet, we can analytically approximate the coefficient of the expansion, and we can compute the autocorrelation function and the amount of evolution for this packet in that infinite well. And although the analysis of the time scale involved in this problem is more complicated or more elaborated than in the previous example, for our purpose, we show the behavior of the measure related to the classical period of the system, and we see that for a time close to the classical period of the system, the measure, the amount of evolution almost reaches its asymptotic value as in the previous examples. And I show you here this last figure, in which we can see that the system even reached an interesting features in the dynamics, such as a revival. Here we have a revival of the system at a time scale which is larger than the time scale in which the measure of the amount of evolution reaches its asymptotic value. So we can safely state that with some relevant aspect of the dynamic of the system are happening, the measure of the amount of evolution is in its or almost is in its asymptotic value. And we will come back on these results for the last part of the talk. So, I will show here a relation with the timeless approach to the quantum dynamics. The time problem is central to modern physics. It impacts quantum mechanics, cosmology, general relativity. We have in the afternoon session of yesterday some interesting talks about time. indeed about the timeless approach also. And in an attempt to incorporate time in a fully quantum context, Reich and Guter proposed this timeless approach in 1993 in this work. And according to this approach or this proposal is based on three main assumptions. We will have a clock and a system, which is the rest of the universe, and the clocks and the system do not interact. The clock provides the parameter T to the system, and the system and the clock are entangled, and the clock and the system as a whole are in an eigenstate of the total Hamiltonian. So in this, according to this timeless approach, the evolution of the rest of the universe, which is the system we call R, reflects the fact that for different states of the clock, there correspond different states of the system of interest, which is all the rest of the universe. While the whole universe, which is this system R and the clock, remain in a single static state. So according to the timeless approach, both the dynamics and time emerge from the correlations between the clock and the system. So this is a scheme. I borrowed this figure for this nice recent paper. Here we have, in this timeline proposed, one considers the whole universe as a closed quantum system, composed by a clock, whose degrees of freedom will be denoted by T, and the rest of the universe, which we call R, with some coordinate X. And well, there is a representation of the clock as a quantum system. Each of these subsystems, C and R, have its corresponding Hilbert space. And this whole system, the universe state, is in a eigenstate of a total Hamiltonian with corresponding eigenvalue equal to 0, consistently with the Wheeler-DeWitt equation. So we consider that this system is described by this function. We can write this expression for the state of the universe, where again here X represents a spatial coordinate or any other degree of freedom of interest of the system, or which can be of one or many particles, and T represent the basic state of a clock, and this is the eigenstate of these are the eigenstate of a clock observable. So I don't go. I won't go deeper with these approaches, but one thing that one sometimes is interested in is in calculate the entanglement between the clock and the rest of the system. As the universe is in a pure closed quantum state, the entanglement can be quantified through the degree of mixedness of the marginal reduced density matrix. So which we do here is compute the reduced density matrix of the system of interest, which is the rest of the universe, tracing over the degrees of freedom of the clock. And we compute the entanglements using the linear entropy. Of course, we can compute the entanglement using the von Neumann entropy, which is the standard measure of entanglement for pure state. But this is also a nice quantifier of entanglement. And if we obtain this for the entanglement of between the system and the clock, and if we compare this expression with our expression of the amount of evolution, we can say that the amount of evolution experienced by a quantum system in a time interval capital T correspond from the timeline point of view to the amount of correlation between the system and the clock. And according which we use our previous results, which we see in the few slides before, as the length of the interval T increases, the quantum correlation between the clock and the system it has the value dl, which is the asymptotic value of the amount of evolution. So just going into the last part, we assume that our measure D is well approximated by its asymptotic value. So we take D equal to its asymptotic value DL. And under this assumption, we now investigate the state that maximize this amount of evolution under constraint of fixed mean energy. So this is now our measure. This is the asymptotic value of the measure. Remember that here we are taking only the first term in the whole expression of the amount of evolution, because we are approximating the amount of evolution with its asymptotic value, because this asymptotic value is quickly reached in the dynamic. So this expression here can be written, because of the normalization condition that satisfies this coefficient, can be written in this way, which can be writing again in this way, now in terms of energy. And here we can identify this probability of getting the particular value of energy EI when measuring the system energy. So we can write this quantity here, or this GL, equal to the linear entropy of the energy distribution. And the linear entropy has a clear statistical interpretation. If one measures the energy of two identical prepared copies of the system, the linear entropy equals the probability of getting different results in these measurements. So in this sense, the linear entropy can be regarded as a measure of diversity in the way that the different energy eigenvalues are represented in the quantum state under consideration. In fact, the linear entropy is used as a diversity index in biology, for example, which is sometimes referred as a Gini-Simpson index. So if we think here in the situation of zero energy diversity, this situation corresponds to an energy eigenstate, which is when the system is in an energy eigenstate, and this is a state that basically that does not evolve. So we now investigate the state that optimize this measure, this linear entropy, and these are the steps that we follow. We approximated the amount of evolution by its asymptotic value, and the asymptotic value of the amount of evolution is equal to the linear entropy of the energy distribution. So we find the optimal state, and this optimal state can be regarded as the state that evolved the most under given energy resources, and have an energy distribution which is given by this expression. And this is a problem of optimization with two constraints, the normalization and the fixed mean energy, and can be usually solved using Lagrange multipliers. But we follow a different path, and we directly prove that this optimal probability distribution, that this is the optimal probability distribution of energy, where here A is a constant of normalization, a factor of normalization, and B is a real parameter with units of inverse of energy. And this is the Heaviside step function. And we prove that between all the probability distribution that satisfies the normalization condition and the fixed mean energy, this is the optimal probability distribution, which maximizes the linear entropy. And we, with this equation, we obtain this relation for the optimal amount of evolution, which resembles this thermodynamical relation between the standard entropy, the energy, and the temperature here. So we can identify that this 2AB plays the role of an inverse temperature-like quantity, and that this optimal measure of the amount of evolution satisfies a kind of thermostatistical relation as the thermodynamical relation, as that well-known thermodynamical relation between the entropy, energy, and beta associated with the canonical ensemble. So, of course, this problem also can be solved using Lagrange multiplier, and this is the variational problem that we need to solve. When here we have one Lagrange multipliers alpha, and the normalization condition, the fixed energy condition. As if we solve this variational problem, we obtain, of course, the same probability, optimal probability distribution. Here we obtain this expression, and we can relate alpha 0 with 2a and alpha 1 with 2ab. And with this method, the cutoff of the probability distribution need to be analyzed. It cannot be derived directly from the solution of the variational problem. So just let me show you the last result. We explore the behavior of this optimal measure of the amount of evolution as a function of the mean energy of the system. And these figures correspond to the examples we saw before, the qubit system, the harmonic oscillator, the 2-qubit system, and the Gaussian wave packet. And the detailed dependence of the measure differ from systems because they have different energy spectra. However, all exhibit a similar behavior. All the measures are the curve exhibiting a monotonally increasing behavior of as a function of the mean energy, which corresponds to a positive value of that temperature-like quantity. And the curve also exhibit a definite concavity, which means that the optimal amount of evolution and the energy resources obey a relation of diminishing returns. That is, as the mean energy of the system increases, further increments of the mean energy are less efficient to increment the optimal amount of evolution. And this is more evident in these two figures here on the left, where we can see that increasing the resources of the system, the optimal amount of evolution increase in a smaller quantity. So to finish, I will show you some discussion. We have introduced this quantitative measure of the amount of evolution. This measure is defined as the time average of the distinguishability between different state of the system at different instant of time in a given interval. We show that the measure depends on the interval only through the length of the interval, which is a kind of a translational invariant property. And we show that this measure is always, sorry, I did forget. This measure is always equal or less than its asymptotic value, and this asymptotic value is equal to the linear entropy of the energy probability distribution, and this asymptotic value is quickly reached in most of those typical quantum systems I show you. And using this approximation for the amount of evolution, we investigate the quantum state that evolve the most under given energy resources. And we find that the relation between the optimal measure and the state is related to the mean energy through a thermostatistical light formula. So that's, I think I will stop here. And
well, thanks, Anna, for your talk.
Thank you for your attention.
Well, now we have
the work, the reference of the work.
Oh, perfect. Well, we have time for questions. We have a question for Martin Bosic. Martin.
Hi, Anna. Thanks for your nice talk. I have a question, a short question, maybe speculative. When you calculate the entanglement between the clock and the system by using the linear entropy. You recover a relation between this entanglement measure and your measure of average distinguishability. Okay. Well, what happens if you use another measure of entanglement? Because for pure state, or entropy are equally, no?
Yes.
You can define another well-defined measure of average distinguishability.
Maybe, I don't know. We don't go deeper in that line, and I don't know what happened, because yes, maybe we can define another measure of the amount of evolution. This is a quite simple measure of the amount of evolution, and this measure is related with the linear entropy of the energy probability distribution, but it's just a proposal. And the things come naturally. Yeah, we define this measure in a very simple way as this time average of the distinguishability, just using this expression for distinguishability. But maybe we can prove another form of distinguishability in terms of another quantifier of distinguishability between the states.
Yes, because my intuition is there is more fundamental structure between entanglement and distinguishability, and more yes, fundamental relation, not only for this particular measure, you know, maybe.
Yes, of course.
Okay, thanks.
Yes.
Well, we have another question from Federico.
Hi, Anna. Thanks for this interesting talk. I have a question about the property of D, which is that it is only dependent on the length of the time interval. But does this property only holds for closed systems, or if you have a system interacting with an environment?
Yeah, I don't know, because we introduced this measure only for a pure system which evolve continually in time, and this derivation are not restricted to a discrete system. It could be any system of continuous variable, but we consider only pure state, and all derivation is in terms of pure state. Maybe it could be an interesting question, and we can work on that idea.
Yeah, because perhaps you can just check it by putting a model and see what happens, right? I mean, for open dynamics. Yeah. Okay, thanks. Very interesting.
Thank you, Fed.